Why are orbital maneuver calculations so complex? Imagine trying to plan a precise dance where every move depends on the last and the slightest misstep can throw everything off. That's what calculating orbital maneuvers is like. It's a puzzle made of many pieces that must fit perfectly. When spacecraft change orbits, they do so by applying small pushes called velocity changes or delta versus. These pushes are carefully timed and directed, but figuring out exactly how much and when to push is no simple task. It all starts with understanding how objects move under gravity, which is described by Newton's laws of motion and gravitation. The spacecraft's path is usually an elliptical orbit, shaped by parameters like how far it is from the planet or star, how elongated the orbit is, and how tilted it is. Changing that orbit involves calculating the right velocity change at just the right moment to reach the new orbit efficiently. One big reason for the complexity is that the equations involved are nonlinear. That means they don't follow straightforward, predictable patterns. Instead, they requiring iterative methods like Newton's method to find solutions. These methods involve making guesses, testing them, and refining until the calculations are accurate enough. This process can be slow or unstable, especially for highly elliptical orbits or when the spacecraft is near a parabolic trajectory. Another challenge is managing multiple orbital parameters at once. When planning a maneuver, you need to consider how to change the altitude, the shape of the orbit, and its orientation all at the same time. For example, moving from a low Earth orbit to a higher one involves calculating the size of the velocity boost needed at specific points, often called burns. Timing these burns precisely is essential to minimize fuel use and ensure the spacecraft reaches the right spot. Gravitational influences don't stop at the main planet. Other celestial bodies like the Moon, the Sun, or even nearby planets can tug on the spacecraft, altering its path. Earth's gravity isn't perfectly uniform either, with variations caused by its shape and mass distribution. For interplanetary missions, the spacecraft leaves Earth's sphere of influence and enters the gravity fields of other bodies, making the calculations even more complicated. Propellant constraints add another layer of difficulty. As the spacecraft burns fuel, its mass decreases, which affects how much delta V it can produce. Engineers use the Tsiolkovsky rocket equation to link the amount of fuel needed to the velocity change required. This means they have to plan maneuvers carefully to avoid running out of fuel before reaching the target orbit. Timing is everything. The spacecraft's position in its orbit determines when a burn should happen. Calculating the orbital period, phase angles, and transfer times requires precise math, especially when dealing with elliptical orbits or rendezvous with moving targets like space stations. Small errors in timing can lead to big deviations from the planned trajectory. To handle all these factors, mission planners relying on specialized software tools. These programs incorporate physics, numerical methods, and spacecraft limitations to generate accurate maneuver plans. They help ensure the spacecraft uses the least fuel possible while hitting the right orbit within the mission's schedule. All these elements, complex equations, multiple parameters, gravitational influences, fuel limits, and timing, make orbital maneuver calculations a demanding task. They requiring advanced math, physics, and computer simulations to get right. That's why they are at the heart of satellite systems and orbital dynamics, demanding careful planning and precise execution to keep space missions on track.